Good morning, everyone. It's a great pleasure to be here today. My name is Gang Li from the Automation and Interventional Medicine Robotics Lab from Worcester Polytechnic Institute. Today, I would like to introduce our study on Fabry-Perot Interferometry-based MRI-Compatible miniature Uniaxial force sensor for the percutaneous needle placement. Percutaneous needle placement, including the prostate biopsy and prostate brachytherapy, is a gold standard for diagnosis and common treatment for prostate cancer. Magnetic resonance imaging is the ideal surgical guidance for diagnostic and therapeutic procedures with its ability to perform high-resolution, real-time, high soft tissue contrast imaging without ionizing. With the guidance of MRI, we can get a very good image, but we need the assistance to make the workflow more effectively. The teleoperation system can resolve that problem, but currently most of the MRI-compatible robotic system lose the tactile feedback. So the goal of this study is to develop a force sensor and to enable the tactile feedback during the teleoperation procedures. The force sensor design in this study is based on the Fabry-Perot Interferometry because of its advantage to provide absolute force measurement, and it minimizes the thermal and chemical change, miniature size, and also for its MRI and biocompatible. Ipf Fiber Sensor is a cavity. Which contains semi-reflective mirrors. The light partially transmitted and partially reflected. The original lens of the cavity is the L cavity, and when there is no force there, and the two blue lines shows a light path. When the external force applied, the change of the lens is 2 delta, and the two red light paths interfered with each other, creating black and white fringes that are different from which created by the blue ones. The intensity of the interfered fringe can be calculated by multiplying the complex conjugate and the Euler identity. So the external applied force can be got by detection of the intensity of the reflected light. The Ipf Fiber sensor we use in the study is made by the Fischer technologies, which can be designed to be disposable. The sensing range is from 1000 macro epsilon to 1000 macron epsilon, and its resolution is about 0.01% of the full scale, and the strain of the false Ipf sensor can be calculated by according to this formula. The Ipf Fiber sensor is designed to be integrated into our teleoperated needle placement robot. The robot consists of a robot controller box, a master device, and a needle placement robot. This figure shows the system set up in a MRI scanner here. The 6-DOF robot needle placement sleeve robot consists of a 3-DOF base modular, which is a decoupled XYZ Cartesian stage, and a 3-DOF needle driver, which can drive the cannular translation, cannular rotation, and stellate translation. To register the robot to the MR scanner to the patient in the patient coordinate system, a fiducial frame is firmly attached to the base of the robot, and the flexure is designed to attach the Ipf sensor and also constrain the motor drive rods to detect the needle insertion force. The flexure is made of aluminum alloy with Young's modular of 69 gigapascal, and the Ipf sensor is firmly embedded in this sensor groove. The intersection points of the sensor groove and the strain enhancement groove is the center of the active sensing range to maximize the sensing capability. Two screw mounts here is used to attach this flexure to the needle driver mechanism. The desired needle insertion force is from 0 to 10 Newton, and the finite element analysis is performed to optimize the design and also to ensure the strain is within the sensing range of the IPS sensor. This figure shows the actual flexure attached with the IPS sensor. A preliminary optomechanical benchtop interface was built to evaluate the concept of design. The dimension of this system is about 80 centimeter times 80 centimeter, which is too big to put into our controller box, which is 40 centimeter times 40 centimeter. So to address this issue, a new compact and portable version was designed based on the same principle. The laser driver can provide constant power, and with continuous laser output adjustment, the light comes out of the pig-tailed laser diode and pass through the cubic-mounted pellicle beam splitter. 2 collimator is placed in horizontal orientation inside this aluminum optical fixture. A 10-meter long optical fiber is connected to the IPS sensor fiber through the FCST connector. The reflected light is detected by the photodetector, and the voltage signal is sent to our controller box. And the dimension of this aluminum fixture is about 10 centimeter times 10 centimeter, so it's small enough to be enclosed in our controller box, with only this fiber coming out. Oh. This is done.
It came back over itself and centered it.
Okay. No. That's we just stop the slide here. Excellent. Okay.
You will be granted with 2 or 3 minutes more, don't worry.
Okay. So the dimension of this aluminum fixture is about 10 centimeter times 10 centimeter, and it's small enough to put into our controller box. So the calibration of this system is conducted by adding standard weights on the flexure. Oh. So the calibration of this IPFO sensor is conducted by adding a standard weight on the flexure. The weight is at to the stage of the IPS sensor flexure is in the same direction, position, and area as the real motor drive rods contact with the flexure. So that the measured force is in the same direction as the real needle insertion force. The calibrated system can be shown in this voltage versus force graph. The blue dots represent actual measurement, and the red curve is the calibrated curve that fits into a sinusoidal function, which is the theoretical relationship between the force and the output voltage. So the root mean square error is about of this calibration is about 0.318 Newton. So this figure shows how this IPS sensor is integrated into our sleeve robot. So the flexure is firmly attached to the needle driver here. It's firmly attached here, and the fiber coming out, the blue fiber is the IPF sensor, is coming out here and connect to our optical mechanical interface. It's set up here, and this interface is small enough and can be put into our controller box. And this system will be put into the MR scanner room. So in summary, in this study, we designed a flexure to attach the IPFO sensor, and we performed the finite element analysis to optimize the design. And a new compact and portable opto-mechanical interface was designed to integrate the IPFO sensor into our needle placement robot. And the IPFO sensor is calibrated, and the relationship between the force and output voltage is established. We also developed a teleoperated MRI-compatible needle placement robot with a tactile force feedback based on the IPFO sensing of the needle insertion force. That's all. Thank you. Next question.